Hello dear students, my name is Vikram Nalode. I am from Mechanical Engineering Department working at the SATCOE at Ravitsalkanji. Today we will discuss some content from unit number 4, joining processes. We will cover about soldering and brazing. So let's start from the overview of brazing and soldering. As we all know, both type of joining processes use filler metals to permanently join metal parts, but there is no melting of the base metals. In both type of processes, they are used instead of fusion welding because metals have poor weldability, so it can be brazed or soldered. Dissimilar metals are to be joined. Intense heat of welding may damage components being joined. Geometry of joint not suitable for welding. High strength is not required. So these are some points over which brazing and soldering, these processes are preferred over welding processes. So here the welding technique is represented by this diagram. Generally, brazing, it is a joining process in which filler metal is placed between the mating surfaces to be joined, and the temperature is raised sufficiently to melt the filler metal, but not the components, as would be the case in the fusion welding here. So, brazing is a liquid state bonding process. Upon cooling and solidification of the filler metal, strong joint is obtained. Filler metals used for brazing, these melt above 450 degrees Celsius, which is below the melting point, solidus temperature of the melt to be joined here. So in this torch is providing the high temperature flame. Filler rod is there. Two different elements, components are to be joined, are shown here. So after using the filler rod, such kind of joint is developed here. So this is brazed joint. So some of the brazing methods are here. So first is torch brazing method. This is similar like oxy-fuel gas welding, in which flames are used. Some proper proportion of oxygen gas and acetylene gases, these are used and supplied through the welding torch. Here this is a job, filler metal is used, flame is here, and this is a job here. So two components are joined by using this technique. This is performed first by heating the joint with the torch and then depositing the brazing rod or wire in the joint. Generally, thickness is in the range of 0.25 to 6 mm. So next is furnace brazing. So furnace brazing, here induction kind of furnaces can be used here. The parts are pre-cleaned and preloaded with the brazing metal in appropriate configuration and then placed in the furnace. Whole assembly is heated uniformly in furnace. Furnaces may be batch type for complex shapes or continuous type for high production runs, especially for small parts with the simple joints design. Vacuum furnaces are used for metals that react with the environment, such as stainless steels, where the passivation layer of chromium oxide can compromise with weld strength. So this is the first diagram, which is before, and this is after, where filler metal joins the components here. So this is an example of furnace brazing, and now we will discuss about induction brazing. Generally, as the picture is clear, for induction brazing, induction heating by means of high frequency AC current is used Parts are first preloaded with the filler metal and then placed near induction coils for rapid heating. Unless a protective atmosphere is used in induction furnace, fluxes are generally needed. So part thicknesses are generally less than 3 mm is used for induction brazing, and generally these are suitable for continuous brazing of the parts. Now next we will discuss about here resistance brazing, and which can be represented by RB. Here the source of heat is through the resistance of components to be brazed. Electrodes are used for this purpose as in resistance welding. Parts are either preloaded with filler metal or filler metal is supplied externally during the brazing. The thickness is developed in case of resistance brazing. It is 0.1 to 12 mm. So process is very rapid. Heating zones can be confined or limited to very small areas, and process can be automated to produce uniform quality. Next is dip brazing. Here the diagram for figure is also present for dip brazing. Dipping the assemblies to be brazed into either a molten filler metal bath or a molten salt bath at temperature just above the melting point of the filler metal, while serves as the heat source, which is heat source here. All workpieces surface are then coated with the filler metal. Debrazing is metal baths is used only for small parts, such as fittings usually of less than 5 mm of thickness. Molten salt baths, which also act as the fluxes, are used for complex assemblies of parts with various thicknesses. Generally, 1,000 joints can be made at one time by dipping in the molten salt bath or molten filler material. Next is infrared brazing, represented by IRB. This process is particularly suitable for brazing very thin components, usually less than 1 mm thickness. Can be used including honeycomb structure. Now the radiant energy of lamp is focused on joint, and the process can be carried out in vacuum. So microwave heating may also be used. So here the quartz lamps are shown here, and these are the parts to be brazed. So this is the technique through which lamp light is focused on the components and raise temperature for almost 1 mm of thickness. Now these are the some designs of brazing components here. As in all joining processes, joint design that is important in brazing. So here in this case, some of the joints are shown here. Different types of structures in different forms. These are joined by brazing techniques. So we can find various applications of brazing technique to join different materials. Here some of the joints which are shown, that which one to choose and which are very poor for their mechanical strength or different factors. So we have some of the points here. First one, this is good design. This is poor design, that too little joint area in shear in the poor condition. So this is the good condition in which components are brazed here. So in this condition, improved design when fatigue loading is a factor to be considered. And here this is a good design, this is a poor design. The bonding area is lesser in the poor design. Now let's compare brazing with the welding. Any metal can be joined, including dissimilar metals. It can be performed quickly and consistently, permitting high production rates. Multiple joints can be brazed simultaneously. heat and power requirement is lesser than friction welding. Problems with the heat affected zone in base metal, these are reduced, and joint areas that are inaccessible by many welding processes can be brazed. Capillary action draws molten filler metal into joint. So these are some of the drawbacks of brazing. Joint strength is generally less than a welding joint. Joint strength is likely to be less than the base metal. High service temperature may weaken a brazed joint, and color of brazing metal may not match color of base metal parts. Possible aesthetic disadvantage. These are some of the applications in automotive: joining tubes and pipes; in electrical equipment, joining wires and cables; in cutting tools, brazing cemented carbide inserts to shanks; jewelry applications; then chemical process industry, plumbing and heating contractors join metal pipes and tubes by brazing; repair and maintenance work. Now we'll discuss about soldering. Soldering is almost similar technique as like brazing, but here filler metal is called solder that melts at a relatively low temperature. As in brazing, the solder fills the joint by capillary action between closely fitting or closely placed components. So here two important characteristics of solders are low surface tension and high wetting capability. Generally, heat sources for soldering, these are soldering irons, torches, or ovens. Here this is the schematic information that soldering iron provide the temperature along with the filler material, that is solder here. This is the copper pad, and the solder iron is used to improve the temperature. Due to solder melts and it joins the materials to be welded in the form of soldering. So types of solders and fluxes. The solder metal melt at a temperature that is at the eutectic point of solder alloy, and I'll tell one example of solder that in which tin is having almost 62% and 38% lead composition, which melts at 188 degrees Celsius, whereas tin melts at 232 degrees Celsius and lead at 327 degrees Celsius. These are some of the types of solders along with the applications. Now fluxes, these are used in soldering and for the same purpose as they are in welding and brazing. Fluxes are of two types: inorganic acids or salts such as zinc ammonium chloride solutions, which clean the surface rapidly. It also avoids the corrosion and flux residues. Then non-corrosive resin-based fluxes used typically in electrical applications. I'll discuss solderability of some of the materials. Generally, solderability is like weldability; it is the ability to get soldered. So different materials have different ability of getting soldered. So here copper, silver, and gold, these are easy to solder. Iron, nickel, these are very difficult to solder. Aluminium and stainless steel are difficult to solder, but because of their thin, strong oxide films. Steels, cast irons, titanium and magnesium, as well as ceramic and graphite can be soldered by first plating them with suitable metallic elements to induce interfacial bonding. A common example is the tin plate, which is steel sheet coated with tin. The making it very easy to solder. Tin plate is a common material used in making cans for food. These are the soldering applications. Various pictures which are showing various joints are developed by the solders here, and the general guidelines are that soldering temperatures are relatively low. A soldered joint has very limited utility at elevated temperature. So moreover, since solders generally do not have much strength, the process cannot be used for load bearing members. These are the advantages: low energy, then brazing, variety of fitting methods available, good electrical and thermal conductivity in joint, easy repair and work, Disadvantage that low joint strength, possible weakening and melting of joint at elevated temperature.